And if this battery is so great, why has it been relegated to probes and satellites so far? And where the heck did it even come from?
In the cold, endless void of space, an idea was born. A machine that could revolutionize energy storage and spacecraft control. A machine so simple, yet so powerful, it could have changed everything. But despite its promise, it was left behind.
Science as much as it was logical leap forward. And the result was an incredibly long-lived, energy-dense, and low-maintenance battery prototype, ideal for satellite-type applications. A few more successful tests and some optimizations later,
NASA's groundbreaking flywheel technology, capable of storing energy with nothing but motion, never made it to the stars. The reason? A twist of fate. A decision that left this extraordinary invention grounded. But what if its true purpose wasn't meant for space at all? What if it was meant to change the world in ways we never expected? In space, the need for reliable energy storage is paramount. Unlike on Earth, where power systems can be maintained or replaced as needed, space missions require a different approach. In the harsh conditions of space, the technologies we take for granted on Earth, like batteries, often fail to meet the demands of long-duration missions. One of the most critical challenges engineers face is how to store and manage energy efficiently in a place where resources are limited and the environment is unforgiving. Batteries, especially lithium-ion types, have become the go-to solution for energy storage on Earth. They are used in everything from smartphones to electric cars, providing a reliable source of power. However, in space, lithium-ion batteries struggle to maintain their performance. The vacuum of space presents extreme challenges for these power sources. Spacecraft and satellites rely on these batteries to provide energy for essential systems, but in the cold vacuum of space, lithium-ion batteries degrade much faster than they do on Earth. When lithium-ion batteries are exposed to extreme temperatures, both in the intense heat of the sun and the freezing cold of shadowed space, their performance drops sharply. Internal resistance increases, and the battery's charge capacity diminishes. What makes this particularly challenging is the unpredictability of the environment. While Earth-based systems have climate control to maintain an optimal temperature, spacecraft in orbit do not have this luxury. They experience rapid temperature fluctuations, often shifting from blistering heat when facing the sun to freezing cold when in the shadow of Earth or other celestial bodies. This rapid change accelerates the chemical degradation inside the batteries, leading to shorter lifespans. Even the best battery technology currently in use on the International Space Station, ISS, designed to withstand these harsh conditions, is not immune to this issue. These batteries are only expected to last around 11 years. Once they start degrading, their chemical reactions become irreversible, and their performance steadily declines. This is a significant issue for missions that could last decades, such as those targeting deep space exploration. Another challenge in space is the inability to easily monitor the health of a battery. On Earth, you can check the charge level of a battery by simply looking at the device. In space, however, determining how much charge is left in a battery isn't straightforward. Engineers rely on algorithms and estimations to calculate remaining power, which introduces a level of uncertainty. These estimations are crucial because, in space, failure is not an option. Even small errors or unforeseen events can lead to the failure of critical systems, which could jeopardize the entire mission. NASA engineers understood that if humanity was to venture further into deep space, they needed to find a solution that went beyond just improving existing lithium-ion technology. The limitations of chemical batteries became clear, and the search for a more robust, efficient solution began. The ideal energy storage system for space had to meet several key criteria. It had to be durable, efficient, and resilient to the extreme conditions of space. Most importantly, it had to be independent of fragile chemical reactions. This led NASA to consider alternatives to chemical batteries. What if the solution to energy storage wasn't chemical at all? What if there was a way to store energy that didn't rely on chemical reactions, but instead harnessed the power of motion itself? The answer, it turned out, could be found in something far simpler but no less powerful: the flywheel. Flywheels had long been used in satellites to maintain orientation. These spinning masses create gyroscopic forces that help control the direction of a spacecraft. The idea of a flywheel as an energy storage device was intriguing. Instead of using electricity to charge a chemical battery, engineers could use it to spin a heavy wheel. The rotational energy stored in that spinning wheel could then be converted back into electrical power when needed. This concept offered a completely new way of thinking about energy storage in space. The flywheel battery system was designed to combine two critical functions into one system. It wasn't just an energy storage device, it could also control the orientation of the spacecraft. This dual-purpose nature of the flywheel made it an ideal candidate for space missions. By using motion to store energy, the flywheel could solve two problems with one elegant solution. It could power the spacecraft systems while simultaneously keeping it stable and oriented in space. This was a new approach that merged energy storage and spacecraft orientation into a single unified system. In terms of design, the flywheel was simple yet sophisticated. It would be made up of a carbon composite rotor, capable of spinning at incredibly high speed, up to 100,000 revolutions per minute (RPM). The rotor would be sealed inside a vacuum chamber, protected from the friction that would normally slow it down. To keep it spinning with minimal energy loss, the rotor would be levitated using magnetic bearings. This would prevent the rotor from making contact with any surface, thus reducing friction to near zero. The result would be a system capable of storing energy for long periods of time with little to no degradation. Electricity would flow into the motor, spinning the rotor and building up kinetic energy. When power was needed, the motor would reverse, becoming a generator, and the rotor would slow down, releasing its stored energy back as electricity. This entire process was incredibly efficient. Up to 90% of the energy could be recovered in a single cycle with minimal loss. Unlike conventional batteries, the flywheel didn't rely on chemical reactions that degrade over time. There was no chemical waste, no toxic materials, and most importantly, no risk of thermal runaway, a dangerous phenomenon that can occur in lithium-ion batteries. This made the flywheel system an attractive option for long-duration space missions, where reliability and efficiency were paramount. The engineering of the flywheel system was also highly refined. Every component was selected for its performance and minimal mass. For example, the copper coils and permanent magnets were positioned with precision to maximize the system's efficiency. The rotor was designed to endure extreme forces, ensuring it could withstand the intense conditions of space. The vacuum chamber, essential for preserving energy, was carefully constructed to keep the rotor spinning for months without significant energy loss. NASA's vision for the flywheel battery was groundbreaking. It represented a shift in thinking from traditional energy storage systems. Instead of relying on fragile chemical reactions that degrade over time, the flywheel relied on the simple, elegant concept of motion to store energy. The flywheel was efficient, durable, and simple, a perfect solution for space. However, despite its promise, the flywheel never made it into space. There were several factors that led to its downfall, not because the technology didn't work, but because the timing was wrong. As the flywheel technology was maturing, lithium-ion batteries were also evolving rapidly. Their energy density was increasing, and their costs were dropping. More importantly, they were already in use and well understood, whereas the flywheel required new systems and more testing. The risk of adopting an unproven technology in a high-stakes environment like space was a major concern. The flywheel system's energy density, though impressive, was still lower than that of lithium-ion batteries. This made the decision to go with traditional batteries an easier one, despite the flywheel's efficiency and dual-function capabilities. In the world of space exploration, simplicity and familiarity often win out over innovation. NASA's search for a better energy solution didn't stop with the understanding of the limitations of lithium-ion battery. As engineers faced the challenges of maintaining power systems in space, they were forced to look for alternative, innovative technologies. This is where the idea of the flywheel came into play. The flywheel concept was not new. It had long been used for a variety of purposes, including the maintenance of spacecraft orientation. But could the same technology be adapted for energy storage? Could a flywheel be used to store energy without relying on traditional fragile chemical reactions? NASA engineers thought so. A flywheel works by storing energy in rotational motion. It is essentially a heavy wheel that spins at high speeds, and as it spins, it accumulates kinetic energy. The faster it spins, the more energy it can store. The concept was simple in principle, but NASA's team saw the potential to transform it into something more. Not only could the flywheel store energy, but it could also be used to control the spacecraft's orientation. The idea was that the same spinning mass that helped maintain the satellite's position in space could also power its systems, creating a two-in-one solution for energy storage and spacecraft control. At NASA's Glenn Research Center, a team of scientists and engineers began to develop this concept into something viable. They imagined a machine that could not only power a spacecraft's systems, but also help control its movement in space. This vision led to the creation of a new type of flywheel battery, a hybrid system that would combine two essential functions. The spinning flywheel would act as a mechanical battery, storing energy in the form of kinetic energy, and it would also serve as a device for controlling the spacecraft's orientation, using its gyroscopic forces. This was an entirely new approach to energy storage in space. In conventional systems, spacecraft rely on batteries to provide power, and separate systems, such as reaction wheels or momentum wheels, to maintain their orientation. NASA's flywheel system combined both functions into one machine, reducing the complexity and weight of the spacecraft. This design not only made the spacecraft more efficient, but it also provided a much-needed improvement in reliability. The way this flywheel system would work was quite ingenious. The core of the system was a carbon composite rotor, designed to withstand extremely high speed. This rotor could spin at speeds of up to 100,000 revolutions per minute (RPM), a staggering velocity that would allow it to store an incredible amount of energy. The rotor was sealed inside a vacuum chamber, protected from the friction that would normally slow it down. To ensure the rotor could spin without resistance, it was levitated using magnetic bearings, which eliminated the need for physical contact with any surface. This frictionless environment allowed the rotor to maintain its speed for extended periods, storing energy without significant loss. The idea was that when electricity was sent into the system, it would spin the rotor, building up kinetic energy. When the spacecraft needed power, the motor would reverse its function and become a generator. The spinning rotor would then slow down, releasing the stored kinetic energy as electricity. This process could provide power to the spacecraft systems, and the amount of power left in the system could be easily monitored by measuring the speed of the rotor. This was a significant advantage over traditional batteries, where it can be difficult to accurately measure the remaining charge. The flywheel battery system was designed to be extraordinarily efficient. Up to 90% of the energy could be recovered in a single cycle, meaning that very little energy would be wasted. This efficiency was a key factor in why the flywheel system was so promising. The system also had several other advantages over traditional chemical batteries. For one, it didn't rely on chemical reactions that degrade over time, which meant it wouldn't suffer from the same issues of performance loss and degradation. There was no toxic waste generated by the flywheel system, and there was no risk of thermal runaway, which is a dangerous condition that can occur in lithium-ion batteries when they overheat. Furthermore, the flywheel system was incredibly reliable. With traditional batteries, engineers have to rely on complex algorithms and estimations to determine how much charge is left. These estimates can be inaccurate and can lead to problems if a spacecraft runs out of power unexpectedly. With the flywheel system, the energy stored in the rotor could be easily quantified by measuring its speed, removing any guesswork. This kind of transparency was crucial for space missions, where failure is not an option and every second counts. The design of the flywheel system was not only efficient but also highly durable. The rotor, made from carbon composite materials, was engineered to withstand extreme conditions. Spacecraft experience intense forces during launch, and the flywheel system had to be robust enough to survive this shock. To account for these conditions, NASA engineers added backup mechanical bearings that would help the system survive the forces encountered during launch. Once the spacecraft reached orbit, these bearings could be retracted, allowing the rotor to spin with minimal friction and maximum efficiency. The vacuum chamber, which was crucial for preserving the energy stored in the flywheel, was also carefully designed. In space, energy retention is vital, and the flywheel system had to be able to store energy for months without significant loss. The vacuum environment ensured that the rotor could spin without encountering air resistance, allowing it to maintain its energy for long periods. NASA's vision for the flywheel battery was truly groundbreaking. The idea of combining energy storage and spacecraft orientation control into a single unified system was a major leap forward. The flywheel wasn't just an energy storage device, it was a system that could make spacecraft more efficient, more reliable, and more capable of handling long-duration missions. The design of the flywheel system, with its simple yet refined engineering, represented a new way of thinking about space technology. Instead of relying on separate systems for energy storage and spacecraft control, NASA engineers had created a hybrid machine that combined both functions. This was not just a technological innovation, it was a systems-level breakthrough that could reshape the way spacecraft were designed and operated. However, despite its promise, the flywheel system never made it into space. The timing of its development wasn't right. As the flywheel technology was maturing, lithium-ion batteries were evolving rapidly. Their energy density was increasing, and their costs were dropping. More importantly, lithium-ion batteries were already in use, and engineers were familiar with their performance characteristics. The flywheel system, on the other hand, required new systems, more testing, and a larger investment of resources. The risk was simply too high for NASA to adopt an unproven technology in such a critical area. There were also issues with the flywheel's energy density. While it was an incredibly efficient system, its energy density was still lower than that of lithium-ion batteries. This meant that the flywheel system couldn't store as much energy in the same amount of space, which was a significant drawback in the space environment where every kilogram counts. In addition, the complexity of the system, with its vacuum chambers, magnetic bearings, and backup components, made it more complicated to implement compared to the simpler, more familiar lithium-ion batteries. Despite these setbacks, the legacy of the flywheel system did not end with its abandonment in space. Instead, its principles found new applications here on Earth, where the flywheel technology would begin to shine in areas like grid storage and solar energy integration. The concept of using rotational energy to store and release power would prove to be just as effective in solving Earthbound energy problems as it would have been in space. NASA's flywheel concept represented an innovative solution to a problem that had long plagued space exploration. By combining energy storage and spacecraft orientation into a single system, engineers had created something that could have transformed space missions. While the flywheel never made it to space, its legacy would continue in new, unexpected ways. It would go on to influence advancements in energy storage, helping to shape the future of energy systems both in space and on Earth. Though NASA's flywheel battery system never made it to space, its legacy didn't disappear. Instead, the innovative design found new life in entirely different environments, particularly in Earthbound energy systems. The technology, initially intended to help power spacecraft and stabilize their orientation in space, turned out to have significant real-world applications in renewable energy and grid storage, helping to address some of the growing challenges of energy sustainability. Once the flywheel system was shelved for space exploration, engineers looked for ways to adapt its principles to more practical, Earth-based uses. One of the first notable adaptations occurred in Ontario, Canada, where the MTO flywheel facility was launched. This facility marked the first large-scale use of flywheel technology to regulate and store energy within a local power grid. Inside the facility, 10 steel flywheels, mounted on magnetic bearings, spun at extremely high speeds, not only storing energy but also smoothing out fluctuations in the grid. This became particularly useful in areas with a high reliance on renewable energy sources like solar power. Renewable energy sources such as wind and solar are becoming increasingly vital in the global energy mix. However, these sources are often intermittent. Solar energy, for instance, is reliant on sunlight, which is unavailable at night or during cloudy periods. This creates fluctuations in energy supply, making grid stability a challenge. This is where the flywheel technology became valuable. In the MTO facility, the flywheels absorbed surplus energy generated during periods of high solar output. When demand surged, or when solar energy levels dipped, the flywheels would release stored energy back into the grid, balancing power and stabilizing the system. This process helped maintain a consistent energy supply despite fluctuations in renewable generation, ensuring that power was available when it was needed most. The flywheel's efficiency and ability to respond quickly to changes in energy demand made it an ideal candidate for modern power grids. Unlike traditional chemical batteries, which degrade over time and require frequent replacement, flywheels have an exceptionally long lifespan. They can repeatedly store and release energy without losing significant performance. This is crucial in the context of grid storage, where long-term reliability is essential. In the MTO facility, the flywheel system provided grid balancing power with minimal maintenance, making it both a cost-effective and dependable solution. Another key advantage of the flywheel system is its environmental. Unlike chemical batteries, which often rely on scarce and toxic materials such as lithium, cobalt, and nickel, flywheels do not produce hazardous waste or require mining operations that harm the environment. The simplicity of the flywheel's design, requiring only a rotor and magnetic bearings, makes it a far more sustainable option for energy storage. As concerns about resource depletion and the environmental impact of traditional battery technologies grow, the flywheel presents a cleaner, greener alternative. As research into flywheel technology continued, advances in material science allowed for improvements in the strength and performance of the rotors. New materials such as graphene and advanced composites enabled the creation of flywheels capable of spinning at even higher speeds and storing more energy. These advancements expanded the potential applications of flywheels, not just for grid storage, but also for use in remote locations, such as isolated research stations, where traditional power sources might not be available. The ability of flywheels to store energy generated by solar panels during the day and release it at night or during cloudy periods provided a consistent, reliable energy source in places where other options were limited. In addition to power grids and remote locations, flywheels are also being explored for use in transportation. For example, in ports, flywheels could be used to store energy generated by cranes or other heavy equipment, which could then be released to power additional machinery or assist in transport tasks. In aircraft, flywheels could act as auxiliary power systems, reducing fuel consumption and improving overall efficiency. This integration of flywheel technology into diverse industries highlights its versatility and potential to revolutionize energy systems across multiple sectors. The flywheel's application in the medical field is also under exploration. Medical equipment often requires a consistent power supply, and flywheels offer a more sustainable, low-maintenance alternative to traditional battery systems. By providing a reliable power source without the need for toxic chemicals or regular replacements, flywheels could improve the sustainability of medical technology while reducing its environmental footprint. The fundamental principles of the flywheel system also continue to influence spacecraft design. Although the system did not reach space, its concepts still hold promise for future space exploration. The idea of combining energy storage and spacecraft orientation control into one system could eventually prove valuable for smaller, more efficient spacecraft, especially as advancements in material science and rotor design continue to push the boundaries of what is possible.